Welcome to Beyond the Brackets. Today, let's begin our journey into ordinary differential equations. Have you ever wondered how can we predict the growth of a population, the spread of a disease, or the motion of a falling object? All these problems have one thing in common: they involve change. And the mathematics that studies change is called differential equations. For instance, suppose a population P doubles at a rate proportional to its current size. We might not know the exact size of the population, but what we do know is its rate of change. This situation is described using ordinary differential equation. P of t, which represents the population at time t, is called the dependent variable. Since its value depends on time, the variable t is independent variable. Now, the rate of change of population is directly proportional to the current population. Mathematically, we can express this as dp by dt is proportional to p. Introducing a positive proportionality constant k, we can write dp by dt is equal to kp. This is a simple example of an ordinary differential equation which shows how population changes with respect to time. Let's now come to the definition. An ordinary differential equation is an equation that involves an unknown function of a single independent variable and one or more derivatives of that function with respect to the same variable. In general, it can be written in this form. Here, x is the independent variable, y is the dependent variable, n is the highest order derivative of y with respect to x. These are all different examples of ordinary differential equations. As you can see, in each of these examples, x is the independent variable. Each equation involves only a single independent variable, and that's what makes them ordinary differential equations. Further, the order of a differential equation is defined as the highest order derivative present in the equation. The degree of a differential equation is the power of the highest order derivative after the equation has been made free from radicals and fractions with respect to the derivatives. Let's understand this with an example. In this equation, as you can observe, the highest order derivative dy by dx is the first order derivative. Since the power of this derivative is also 1, the degree of the differential equation is 1 as well. For the second example, the highest order derivative here is d square y by dx square. So the order of this differential equation is 2. The power of this derivative is 1 and therefore the degree of this equation is also 1. For the third example, the highest order derivative present is the first derivative dy by dx. The order of this equation is therefore 1. Since the power of this derivative is 2, the degree of the equation is 2. For the fourth example, before finding the order and degree, we need to remove the fractional power. To do that, we first rewrite the equation in a suitable form. Then by squaring both sides, we get dy by dx is equal to y square. Now the equation is free from fractional powers. Here the highest order derivative is dy by dx, so the order is 1. The power of this derivative is also 1, which means the degree of this equation is 1. Moving on to the last example, once again, before finding the order and degree, we first rewrite the equation, then square both sides to remove the fractional power. After simplification, the highest order derivative is dy by dx, hence the order of the equation is 1, and since the power of this derivative is 2, so the degree is 2. You'll also find a few additional problems provided for practice along with their solutions.